What specific problem does the follow instructions with social and embodied reasoning FISER framework aim to solve in the context of human-robot interaction, and how does it differentiate itself from conventional grounded language learning methods?
The follow instructions with social and embodied reasoning FISER framework aims to solve the problem of translating ambiguous natural language instructions into executable actions for robots in human-robot interaction scenarios. Unlike conventional grounded language learning methods, which typically focus on directly mapping language to actions without considering the human's intentions, FISER explicitly incorporates the human's underlying goals and intentions as variables in its reasoning process. This framework decomposes the task into two distinct phases: social reasoning, which infers the subtask the human is requesting based on context and historical actions, and embodied reasoning, which involves planning and executing the robot's actions. By recognizing the inherent ambiguity in human communication and leveraging additional context, FISER significantly improves the robot's ability to follow instructions that are often incomplete or unclear. This structured approach contrasts with traditional methods that overlook the collaborative nature of human-robot interactions, leading to enhanced performance in complex instruction-following tasks.
How does the FISER method work? Illustrate the steps involved in the framework, particularly focusing on how social reasoning and embodied reasoning are separated and applied. Please provide a detailed breakdown of the two phases involved in the methodology.
The follow instructions with social and embodied reasoning FISER method operates in two distinct phases: social reasoning and embodied reasoning. In the social reasoning phase, the robot first disambiguates the natural language instruction given by the human by predicting the specific task it needs to perform. This involves two key functions: task recognition (TR), which interprets the instruction based on the current state and the human's historical actions, and plan recognition (PR), which infers the human's overall plan (H) to identify the subgoal P** that the human is asking for assistance with. Once the robot has established the task it needs to execute, it transitions to the embodied reasoning phase, where it engages in grounded planning. Here, the ambiguous instruction is replaced with the clearly defined robot goal G**, allowing the robot to determine the sequence of actions A_T it must take to achieve the task. This separation of social reasoning, which focuses on understanding human intentions, from embodied reasoning, which deals with executing actions in the environment, enhances the robot's ability to follow ambiguous instructions effectively. Overall, the FISER framework emphasizes the importance of intermediate reasoning about human intentions to improve performance in complex instruction-following tasks.
Can you provide a simple yet illustrative example that demonstrates how the FISER framework translates an ambiguous natural language instruction into executable robot actions? Walk through the main algorithm steps with this example.
Consider the ambiguous instruction: "Could you pass that from the sofa?" In the FISER framework, the process begins with social reasoning, where the robot first analyzes the instruction alongside the human's historical actions, e.g., the human previously gathered books. The robot infers the human's underlying intention, recognizing that the human is likely asking for a book to be placed in a box. This leads to the identification of the subgoal, e.g., passing a specific book, and the robot's task, e.g., handing over the book. Next, the framework transitions to embodied reasoning, where the robot uses the identified task to plan its actions. It checks the current state of the environment to locate the book on the sofa, and then executes the action of moving to the sofa and passing the book to the human. This step-by-step approach, separating social reasoning from embodied reasoning, allows the robot to effectively handle the ambiguity in the instruction by leveraging context and prior knowledge about the human's actions.
What are the theoretical and practical benefits of using the FISER framework over previous methods, particularly in terms of handling ambiguous instructions in real-world scenarios?
The FISER framework offers significant theoretical and practical benefits over previous methods by explicitly modeling human intentions and separating social reasoning from embodied reasoning. Theoretically, it enhances the robot's ability to disambiguate ambiguous natural language instructions by leveraging the context of the human's historical actions, allowing for a more nuanced understanding of the task at hand. Practically, this separation leads to improved performance in real-world scenarios, as evidenced by the framework's 64.5% success rate on the HandMeThat benchmark, outperforming end-to-end methods and demonstrating that intermediate reasoning about human intentions is crucial. Additionally, the inclusion of a human plan recognition stage further aids in complex or ambiguous tasks, enabling the robot to make informed decisions based on inferred goals rather than solely relying on explicit instructions. Overall, FISER's structured approach allows for more effective collaboration between humans and robots in dynamic environments, addressing the inherent ambiguities present in everyday communication.
How is the effectiveness of the FISER framework validated? Discuss the experimental design, datasets used for testing, and the metrics or benchmarks employed to assess performance.
The effectiveness of the FISER framework is validated through experiments conducted on the HandMeThat HMT benchmark, which presents a challenging environment for ambiguous instruction following tasks in a text-based household setting. The experimental design involves training a transformer-based model from scratch and comparing its performance against multiple competitive baselines, including state-of-the-art prior work on HMT and a chain-of-thought prompting approach using GPT-4. The HMT dataset is divided into 4 difficulty levels, with Level 1 being a pure planning task, and Level 4 containing inherent ambiguities that require strong prior knowledge of human intentions. Performance is assessed using success rates in achieving the robot's goals, with the best-performing Transformer plus FISER model achieving a 64.5% success rate on average, thus establishing it as the state-of-the-art on the HMT benchmark. Additionally, the evaluation metrics consider the number of steps taken by the robot, ensuring that the models are not simply improving success rates through brute force methods.
What specific results were achieved through the FISER framework on the HandMeThat benchmark? Highlight key performance metrics and how they compare with existing state-of-the-art methods.
The FISER framework achieved a 64.5% success rate on average in the HandMeThat benchmark, marking it as the state-of-the-art performance for this task. This result was obtained through a transformer-based model that effectively separated social reasoning from embodied reasoning, which significantly improved performance compared to end-to-end methods. Additionally, the FISER framework demonstrated that explicitly modeling human intentions and recognizing the robot's task led to better outcomes across all difficulty levels of the benchmark. In contrast, smaller, more efficient transformer models trained from scratch outperformed state-of-the-art pre-trained large language models, LLMs, by approximately 70%, indicating that pre-training alone was insufficient for complex social and embodied reasoning tasks. Overall, the empirical results underscore the effectiveness of the FISER framework in addressing the challenges posed by ambiguous natural language instructions in collaborative human-robot environments.